So tonight we're going to be moving on from where we left off. We went through antiquity all the way up to about the early to middle Renaissance era last time, set the foundation, and what we're going to do tonight is more or less chronologically move from that era up to roughly the modern day and look at how disease and health itself have been conceptualized and how the changing ideas of what health and disease actually are have developed and matured into what we have now, which we largely call pathology, although we'll have a few branches that work towards surgery and some other issues, but we'll have pathology as the main topic for tonight. So, when we left off, we had gotten some disease classification systems started. Back in the Islamic empires, we had gotten a bit more rigor ascribed to keeping symptoms charted and figuring out which symptoms correlated with what other symptoms so that you could actually tell one disease apart from another. Progress came thereafter in the European universities, but largely in Italy, France, and Germany. And that's going to be where we spend most of our time this evening, working at the universities and hospitals there as we move from a very poor understanding of how the human body works to a very intricate understanding of not just the body, but the organs, the tissues, the cells, and at the end, things that are even smaller than the cells. So disease was thought to be caused by humoral imbalance, but no one really went into any detail on what this kind of imbalance of the humors would actually do to the body, what those effects would be, and why it happened. One popular theory was that there were miasmas, or bad airs, that would come in and disrupt the body's humoral balance. Something called contagion, which is just basically a rough idea that, well, sick people tend to get people near them sick, so we know they're passing it somehow, but there's really no idea, not even an inkling of germ theory or the spread of disease through aerosols, things of that nature. And the idea that disease was a spiritual judgment has stuck around from ancient times up till now, unfortunately, that you're being punished for something by getting that disease. Humoral imbalance is at the root of it all, and diet was one of the things that people thought might be causing disease. And this, I want to just note, people weren't always wrong. In antiquity, they weren't always wrong about things. Diet does actually make a big difference. And while miasmas don't cause disease directly, if you're living in unhygienic, bad conditions, you are probably likely to develop some disease. And so how we take those little clues and actually build a functional system of pathology out of it is pretty fascinating. Near the end, we talked about Andreas Vesalius, who started describing the human body accurately. Some of his notes are thought to have contained notes on how disease progressed, and the donors, well, pardon me, they were not donors back then, how the executed criminals that he dissected were sometimes evidencing some pathology. He could see evidence of some diseases, but sadly he threw a hissy fit when he left Padua and burned all of his notes, so we really have no idea what happened and what his observations there would have been. The first real name that we come up in classification of disease in Europe is this guy, Girolamo Fracastoro. And anybody here done research? Dr. Morris-Wyman, I'm hoping you raise your hand. Yeah, Dr. Thatcher, good. So, standard today is to publish your research in an academic journal, but if anybody here really wants to reach for the stars, I challenge you to make a medical discovery that you publish as a long-form poem, because that's what he did. This is syphilis, and it's the first time syphilis was actually described correctly. It was about a shepherd who developed syphilis, and Fracastoro actually described the progression of the disease accurately and how this guy got it as a curse from Apollo. Okay, that part's not accurate, but he actually typified the disease, how it spread, how it developed in this poem. I should mention I've got an upper respiratory thing. If I make some disgusting noises while I'm talking, my apologies, but there we are. So Jean Fresnel was one of the next big names that came up, and he wrote a book linking some of the observations he made clinically with development of disease to what the findings might be when this person was autopsied. It's no mistake that the understanding of disease came about as autopsies not only became more common, but almost normal procedure in certain hospitals and certain universities. So he had a very intricate and frankly kind of bizarre by our standards development of classification of diseases. He called them general, things like fevers, or specific, things like tumors that were located in one spot. And then he had classified them as above the diaphragm, below the diaphragm, on the outside. So it's not a system that we would adopt now, but it was something. And a lot of times in the history of medicine, something is better than nothing because something becomes a basis that a better piece of work will be built on. So don't ever think that just because they got it wrong means that they were somehow imbeciles or they weren't doing it correctly. It's very hard to come up with knowledge based on nothing. Now, as the anatomy faculty at various hospitals and universities started doing more and more dissections, they started to find that the diseases that they would see kind of clustered in certain areas. They weren't just, you never saw a humoral imbalance. No one ever saw too much black bile. They saw tumors, they saw fractures, they saw infections, and they started actually making pathological atlases. That's one of the things that this guy, Marco Aurelio Severino, was known for, was actually describing what he saw in practice and during the autopsy. And Italy became one of the main places where this is going to happen pretty regularly. And I want to mention that he had the opposite problem that you guys do. When you're in the anatomy lab, all of our donors are largely people who are at the end of life because they had to donate their body. They had to be planning for that eventual end. And so largely, they are people who have pathologies. They have disease, sometimes multiple diseases that you see evidence of. Back in these days, these people were largely forced to work before autopsies became common with the executed criminals who tended to be younger, tended to not have pathologies, and he was actually bemoaning the fact that they never got to see a disease of long standing in one of the people that they were dissecting. They thought that was something that would really help them. So when you're in the lab and you get to MSK soon, look in your direction first years, and you're upset that the muscles are all kind of small and atrophied, just remember you will actually get to see some evidence of disease, and that's kind of the payoff for the system that we have now. Now, Franciscus Sylvius was another person who had a little bit of a jump ahead of time. He worked in a chemical laboratory and really tried to bring a chemical approach to medical treatment and understanding about how the body worked. He was a very fierce advocate of William Harvey's circulation of the blood and really tried to make sure that people saw the benefits that that discovery could bring to medicine. And he believed that the body had, and the blood itself had, acidic and alkaline aspects to it, and you needed to keep those in balance if you wanted to remain healthy. And a little bit of a spoiler for first years, it does. And we have both metabolic and metabolic and respiratory methods of keeping our pH in balance, not getting too acidic, not getting too alkaline, but staying right in that happy area. Now, when you guys think of pathology, and I hope the pathologist in the audience doesn't jump in with the right answer. When you think of pathology, what piece of instrumentation do you think of? Microscope, exactly. So microscopes started to become a thing in the 1600s, and Marcello Malfighi was one of the early adopters of it and looked at tissues to see what was there. And this is where Harvey's theory on the circulation of blood was really kind of backed up. He had hypothesized that there were capillaries or little channels connecting the arteries at their smallest level to the veins at their smallest level, but he never saw any. Malfighi did, and he wrote it up. And microscopy became very important in a lot of different investigations, a lot of it in Europe with Robert Hooke, Joseph Lister, who we'll hear about when we talk about surgery. But the microscope became more and more prominent in anatomical understanding of how the body works. Now, as that was going on, more and more autopsies were being performed at hospitals, and people were starting to develop large collections or compendia of pathological findings. The first major one was called, it's got a great name, it's Sepulchridum Sive Anatomica Practica et Cadaveribus Morbo Dentatis, basically the investigation of cadaveric disease after death. In this, Théophile Bonnet described over 1,700 different diseases, but here's the problem. Each chapter was not organized in any way, shape, or form. You didn't really know where to go looking for things. And if you want to use pathology as a guide to clinical practice and development of disease, you actually need some way to classify it. So that had to wait until another person, an Italian named Giovanni Battista Morgagni, wrote another book with another great name, De Sedibus et Causibus Morbororum, on the seats and causes of disease. Now, he had started with his mentor in Padua, in dissecting pretty much anyone who came through their hospital and died. And they charted the person's arrival, their progression, and the findings at autopsy. And one really spectacular thing is he actually took steps to isolate himself from the more disease-ridden people that they had there. So if someone had died of anthrax, he waited a while to dissect them, tried to make sure that he wasn't in direct contact with any of the diseased tissues, and kind of kept himself at a distance, not out of being dainty, but because he thought something might be wrong with them. And he, over his entire career, kept these notes and wrote up his findings and basically said, I should mention, not only wrote up his findings, but he had a very massive comprehensive index associated with it. And when he wrote the book, the Sedibus, people bought it like crazy. It was a huge hit because doctors could then take this book, and if your patient had a fever, you could flip to the index and look up any pathological case description with fever and start to see if something in there correlates to what you're seeing with your patient before they pass or before it gets too far along. Now, his major finding was that when you're dissecting and looking at these diseased organs, you don't see mislabeled humors. You don't see humors out of whack. You actually see the organs. And he said that the organs were the seat and the cause of disease. That's where the actual problems were arising. And this was really the first nail in the coffin of humoral theory. It wasn't the humors that were unbalanced, it was specific organs having specific problems at specific times that caused the issue. So, we move a little further ahead, and France had not really been much of a player in this. A little bit, but not so much. That actually changed with the French Revolution, and unlike most things with the French Revolution, it actually got better, in a way. It got better because the French, like the Austrians and other people, had a very rigid, hierarchical system in their universities and in their hospitals, and you didn't want to shake the boat. You didn't want to make too much noise. You didn't want to upset your superiors. You certainly didn't want to question their beliefs and their findings about what they were working on. But when the French Revolution came along, all the people in high status positions anywhere in French society were largely booted out and replaced by younger people who were allowed and encouraged to explore and look at new ways of finding things. Now, I don't want to paint an overly rosy picture of the French Revolution by any means. In fact, Antoine Lavoisier was killed by the guillotine because he was considered to be kind of a sympathizer with the king. But it did allow people to break out of old habits, and instead of having surgeons and physicians rigidly separated, a new title was made, and it was just called health officer, and encompassed both aspects of it. So some things did get a little bit better, and France became a little bit more of a player in medical research thereafter. And two of the main figures are these guys, Marie-François Xavier Bichat, and in the middle, Jean Crovalier. These guys took the next step from Morgagni. Morgagni had said that the organs were where he saw disease. These guys found that when you had diseased organs, the texture of them was off. There were certain areas where the texture was bad, things looked a little bit wrong in some areas, and what they were really describing were what we call tissues now, collections of cells that contribute their organization to do a specific job. And so they found that the tissues were where the diseases were manifesting, and like any good person taking a step forward, they described it, did microscopic studies, and wrote up journals and wrote up books, atlases, and these were actually some of the first colored atlases. So you can see some of Cruvalier's atlas pictures there. I think that's, I'm going to mess it up. Somebody feel free to jump in and help me if you can. And it's not endocarditis, it's something else. Go for it. Pericarditis, thank you. When you go blank in front of a bunch of people in a room and you're talking on the stage, you don't stop being blank, you stay blank. So call on the audience. They generally know what they're talking about. It's good. All right, moving on to how disease spreads, our next character is actually John Snow. Sorry, not that one. That John Snow knows nothing. This John Snow actually knows some good stuff. So he had a very interesting career, and we'll bring him up again in surgery, but his big contribution, probably the most important thing he did, was he tracked an outbreak of cholera in London. And cholera is a disease, if you don't know, that's spread through contaminated water. People drink contaminated water that's contaminated by fecal material. They get sick. The sickness causes them to have a great deal of watery diarrhea, which spreads the disease even further. The outbreak was only occurring in certain areas, and he did a lot of work and did the first real, what we would consider modern type of epidemiologic study. And he charted where the outbreak was happening, which houses were affected, and he kind of got a sense that there was one water pump in the Broad Street that was the cluster for it. And when he found people sick nearby that probably would have used a different pump, he sometimes found that they would actually walk to Broad Street to get their water, and that pump was the locus of the outbreak. So he did the most sensible thing. He had the city shut the pump down. They ripped it up and found that there was indeed a sewer line that had ruptured and was spilling into the water that was being pumped out for people to consume. Yeah, sanitation's a good thing. So that's the first epidemiologic study we can really cite about how disease can spread. And keep in mind, he did not know anything about germs. He didn't know that there were microscopic organisms per se. He just knew that the locus of disease was around that pump and something was contaminating it one way or the other. Now, jumping back to pathology and anatomical pathology in particular, in Austria, a massive hospital called the Allgemeines Krankenhaus was built, had several wings, and it was standard practice there that every single person who passed away at the hospital would be autopsied. And the first person there who kind of ran the pathology was right here. This is Karl Rokitansky. So Karl Rokitansky was a good pathologist. He was very interested in microscopic studies, but he got very intrigued by what was happening outside of the cells. This was when cellular and tissue pathology was really ascendant, and by looking at the outside of cells and talking about what he called the extracellular milieu, he kind of fell out of fashion, became kind of a punching bag for other pathologists, and some of his contributions were not really appreciated as a result. Being ahead of your time is not always a good thing. But he did have some very good insights, and one thing, my particular favorite piece of trivia regarding him, that's Karl Rokitansky, and this is Mad Max Rokitansky, named for Karl Rokitansky. So George Miller, the guy who directs the Mad Max movies, is a medical doctor. So he actually financed the first Mad Max movie by pulling extra shifts in the ER in Australia, and because of that, there's little medical tidbits scattered throughout Mad Max, like he has ptosis and a blown out pupil and stuff like that. So just enjoy that, from Austria to Australia to a post-apocalyptic wasteland. Good times. Now, the Allgemeines Krankenhaus is also where one of the more dramatic things in the history of medicine happened, and sadly doesn't have a good ending. A Hungarian obstetrician named Ignaz Semmelweis had noticed a really upsetting discrepancy. There were two obstetric wards where women would give birth. One was run by midwives and had kind of a mortality rate around 3%. About 3% of the women who gave birth in that ward, that one side, a separate building, would die. Whereas the other side, which was attended by physicians, had roughly a 20% mortality rate. And so 1/5 of every woman who went into that building would die. And they largely died of what was called puerperal fever, childbed fever. It was basically a massive infection of the uterus, the reproductive tract, and this is before germs. People don't know anything about germ theory, no concept that these little organisms are hanging out and can actually cause problems. But Semmelweis was not satisfied with the explanations that were being given, that there's a swamp closer to the doctor's wing and that bad air must be getting in, causing the disease. There's all this other stuff. It's not really something we can do anything about. So he noted that the midwives did not do autopsies. And when the physicians who did do autopsies they did them first thing in the morning. And they immediately went upstairs and started doing pelvic exams on all the women in that ward. And it's almost, I'm amazed that 20% was the rate of infection. I would have thought it would be much higher because it's almost a system guaranteed to spread disease from one person to the next. So he instituted a hand washing policy. And what do you think happened? Yeah, the mortality rate went down to 3%, exactly equivalent. Now, at this point, we should be celebrating, we should be happy, but we don't get to be happy. Semmelweis was a very poor communicator. He didn't put his ideas forth in a way that kind of made people understand it. He got very defensive, and he was operating in the Austrian hospital hierarchy, and it was very rigid, and he did not do a good job of working to get his ideas accepted. And so he eventually quit, and the institute went back to the old practices. The mortality rate jumped right back where it was, and nobody seemed to be too upset by this. It wasn't until more junior people who had worked with Semmelweis and understood that he was onto something got in, and maybe decades later instituted those hand-washing policies. So we had multiple decades, not just in the world, but at this hospital in particular, where we could have been saving lots and lots of lives. Semmelweis eventually suffered from dementia, and he was actually put into an asylum for the destitute. And there's a story that goes around that he actually died of infection from a cut finger, as kind of a poetic kind of echo of his findings. Sadly, an actual autopsy done recently on his body, the remaining bones, shows that he was probably beaten to death by the orderlies at this insane asylum. So yeah, not pleasant in any way, shape, or form. Now that's bad, but one other bad thing is there's an American anatomist who taught at Harvard named Oliver Wendell Holmes. He was a huge celebrity back in the late 1800s. I really doubt any of you have heard of him. You might have heard of his son, Oliver Wendell Holmes Jr., who was a Supreme Court justice. But this guy was not just an anatomist and Harvard professor. He had a newspaper article called The Autocrat of the Breakfast Table that was published in pretty much every newspaper, read by everyone in the country practically. He had discovered that hand washing would help stop puerperal fever as well. But he didn't get much support for it when he was in medical practice and kind of dropped it. It just blows my mind. He had this amazing discovery that could have saved all these lives. He had this huge platform from which to air that, and yet it didn't happen. We had to wait until germ theory was established before hand washing, of all things, became standard of practice. So we're going to stick around Vienna for a little while because in addition to anatomical pathology, cellular pathology, we're moving from the tissues to the cells, really took off. And there's a nice lineage of pathologists here, starting with Johannes Peter Müller. He's credited with coming up with the idea that tumor cells are in fact modified regular cells, that tumor cells are not something completely alien to the body or not some weird network-like growth that's just kind of taken off and attacking the body, but it's from actual cells of the body. He did other things as well, but that's one of the major contributions I think is pretty interesting. And the more historically kind of impressive thing he did was he trained lots of students who did some pretty amazing things in their own right. Now, these names might look familiar. You might have heard of Schwann, of Schwann cell fame. He is the person who basically laid down that all animals are made of cells. We didn't know this before. If you go looking for cells in an animal, any animal, you'll find them in those tissues, or at least cellular products like keratin, hair, fingernails, dentin, etc. He was put onto this by a friend of his who is named Schleiden, who had discovered the same thing in plants, and he was very, very interested in botany. He didn't have time for animals, so he just told Schwann, yeah, I bet if you go look in animals, you'll find that they're all made of cells too. And sure enough, they were. Next up, we have Henle. So Henle, as in loop of, discovered a lot of kind of smaller things, but the main contribution he had was he came up with the standard histologic terminology that we use. So when we talk about squamous, transitional, stratified, this is the guy you can thank for that. Exactly. There's some histology hand motions going. If we haven't out taught histology by hand puppets yet, we need to find a way to make that happen. And last, and absolutely not least, is Rudolph Virchow. And Rudolph Virchow, I don't even know where to start. Okay, so let's talk. Take a deep breath, because you're all about to feel incredibly insignificant. I'm in the same boat. So Virchow studied under Müller when he was 22 and became an assistant prosector in the hospital at the Charité in Berlin, 23. At 24, he identified and described leukemia. Then he graduated from medical school. He founded a new journal thereafter simply to have a way to publish all the findings he was coming up with. It was too much of a hassle to submit articles other places, so he came up with his own journal almost exclusively to document what he was working on himself and with a few colleagues. He was actually dispatched to write up a paper regarding a typhus epidemic in a rural part of Germany, and he actually came back with a scathing indictment of the hygiene there and how the government was lax in keeping people healthy through proper hygienic measures. This made people mad. Austria is a very hierarchical, very kind of conservative culture at the time. And he was basically kicked out of Berlin, and he went to work as a pathologist in a hospital in Würzburg. But eventually his fame and just pure volume of work made it impossible for him to stay out of the limelight, and he was brought back with an endowed chair to the University of Berlin and at the Charité Hospital, and remained working there, throughout his life. So, impressive, right? Okay, hold up. He wrote more papers in anthropology than he did in medicine, so he did a lot of work in anthropology. He did a lot of public health works. He was a very staunch proponent of public health practices. Berlin had the worst sewers in Europe. When he lived there, and by the time he died, they had the best sewers in Europe, largely on account of him just pushing and pushing and pushing for public hygiene measures. And because he was such an outspoken social reformer, he was also interested in people's well-being. His anthropologic studies really contradicted the anti-Semitic and racist anthropology that was just standard at the time, and he made a lot of enemies that way. It's actually said that when Adolf Hitler came to power, he lost no opportunity to just verbally abuse Rudolph Virchow at any chance. So if you live a life that makes Adolf Hitler hate you, well done. In addition to Hitler, he had some enemies in his own time. Anybody know who the guy with the spiky hat is? Bismarck. Bismarck was a very conservative, very pro-military German general, and he got very irritated with Virchow and actually challenged him multiple times to a duel. Now, Virchow never took him up on the duel, but he did say, okay, we'll duel, but it has to be with scalpels. Or he said, I'll take typhus and I'll inject it into a sausage, and we'll each pick a sausage at random, and whoever dies, dies. So that was not quite grandiose for Bismarck, so the duel never actually happened. And one last thing, if you don't feel like he's obviously just way outclassed everybody you could ever think of, he was there when they discovered Troy, so I don't even know. So essentially, that's what Rudolph Virchow did. You'll notice a lot of things are named after him, a lot of Virchow's this, Virchow's that. And even though we don't like to use eponyms anymore, at least he earned it. You can see Virchow's name attached to something like, okay, solid guy. Now, Louis Pasteur was not a physician. He was a scientist, but he had arguably some of the most impact in medicine because he was one of the early and most vocal proponents of germ theory of disease. Now at the time, spontaneous generation was considered to be how a lot of things came to life. Vermin just spontaneously developed from rotting food. They literally thought that rotting food produced flies or that hay produced mice. They just spontaneously generated from it. And Louis Pasteur took meat and let it rot, but he made sure that it was kept under glass. And he showed that if the glass had been sterilized, the area had been cleaned, germs couldn't get to it, the meat would not in fact rot. He even showed that it could be open to the air so long as there was a connection that didn't allow dust to settle on the meat, and the meat would still not rot. So he really worked hard to make sure that people understood that germs were responsible for various processes, and came up with pasteurization, no big surprise there, to kill germs in food. He did that after he saved the French wine and silk industries, which were experiencing blights caused by microorganisms. He took the microscope out and was actually able to isolate what things like yeast were present in good wine and bacteria that were present only in the spoiled wine. And he did similar things with the silk industry as well. So he applied microscopic findings to health matters. And the best thing about Louis Pasteur is that not only did he use the microscope and did he have all these insights, he was a phenomenal communicator. Now he's getting a lot of bad press for being a showman, for sometimes stepping on other people's ideas. But the one thing you should take away from Pasteur is that he demonstrates the importance of actually communicating your ideas well. It's not enough just to be right. You have to be right and let people understand that you're right about something. Otherwise, a really good idea can languish and disappear. Now, we know, pardon me, we now know that there are germs. At the time they called them entomolecules, which is kind of a nice term, but there are microorganisms present that can cause disease, cause things to rot, and then the big step forward was figuring out which organisms cause which disease. It wasn't actually clear at some point whether they just caused a variety of diseases or if certain microorganisms cause specific diseases. And Robert Koch came up with a listing of steps to take to demonstrate that a disease is caused by one organism in particular, called Koch's postulates. This is anthrax. It's the first disease that was assigned a specific microorganism as its cause. And you can show that that microorganism causes that disease and no other microorganism does. And at that point, a huge amount of research was done looking for various diseases and the microorganisms responsible, and a ton of descriptions came out about that. Now, some diseases still flustered people. Tumors are not caused by that, but people looked for microorganisms causing that. Viruses can't be seen under the microscopes. Even though viruses are also microorganisms, they're not something that they could observe, and a lot of people were flustered by looking for the causative agent, and there was a causative agent there, but it was viral, and they couldn't spot it with the material they had at the time. Now we're going to shift gears a little bit and talk about concepts of thought and mental activity, because these changed a lot as well. Now, from prehistory on, we've known that the brain and the mind are somehow connected. That's why trepanation occurred. Trepanation occurred because people's brains caused some change in their behavior. And people had noticed that if someone suffered a big head injury, their behavior could get radically different. But no one really knew why. And one of the early and terribly wrong things that came about in this era was phrenology. So Franz Joseph Gall basically came up with this sham science of phrenology out of nowhere and basically said, yes, the brain has certain mental organs devoted to different areas of activity in our life, and when the brain has an enlarged mental organ, it causes a bump on the skull, and I can palpate the bumps on your skull and tell you what you're particularly good at. And they kind of came up with profiles of people who were criminal or people who were cheaters or people who were noble based on their skull bumps. And by the 1840s, it had pretty much been discredited because, thankfully, at this point, science was an actual thing. There were practicing scientists. People had a method to examine claims of this nature. That actually happened again in France with Franz Anton Mesmer and Benjamin Franklin. That'll be next week's talk. We'll be in there. But essentially, phrenology was exposed as being nothing more than made up. And it was largely just based on racial, ethnic, and other prejudices at the time. The problem is, when people make a correction to something, they tend to overcorrect. And at this point, the assumption became that the brain was a network, and it was all interconnected. There was no localization at all. And even though phrenology was bunk, it was right about there being localization, not under these mental organs, and certainly not about changes in the skull as a result. But the brain does actually have regions that are responsible for specific activities. Now, the first real event that led down that pathway was going to be what was called the Phineas Gage incident. Has anyone heard of this already? Several? Okay. Oh, I'm so happy for those of you who haven't heard of it before. Okay, here we go, story time. So Phineas Gage was a foreman on the railway, and they were blasting out rock to lay down a railway. So some person would drill a hole into the rock, another person would come by and fill it with gunpowder, another person would put some tamping material down, and Phineas Gage, the foreman, had a big tamping rod that he would then tamp it down with, and so they could detonate it later, and it wouldn't just flash out of the hole, it would actually be directed into the rock more efficiently. At some point, the person in front of him missed a hole and didn't put the tamping material down, and Phineas Gage plunged it in, and it ignited, and his tamping rod, which is about 4 feet long and actually sharp, shot through his jaw and out the top of his skull. And this is his skull. It's at the Harvard Medical History Museum. And you can actually see, if you're there, the skull next to the rod that actually went through his skull. He kept it. And by telling you he kept it, I'm telling you he lived. He lived through this experience and somehow lived through what, the almost inevitable infection that would have followed. He lived, and he had intact memories. He had the intact ability to speak, formulate thought, understand people, but his personality had completely changed. Now, the traditional story is that he was just unreliable and violent and crude, and there was some truth to that, but over time, he became more capable of operating. He actually worked as a stagecoach driver, so he was able to hold positions, do meaningful work, but his personality had changed pretty remarkably, and it was strictly due to the skull fracture, and more particularly, the brain that had been disrupted underneath. I should mention, it's at the Harvard Medical History Museum, which sounds phenomenal, and it's got this cool stuff there. It's a hallway. It's just if you go to the Quad building here and just put a bunch of really cool things in cases, there we go. That's the WSOM Medical History Museum right there. It's just their hallway. It is cool, but there we go. So, localization of function became something people started looking for, and they started to see that the brain was not this uniform reticulum of activity. It was localized in different spots. Paul Broca found a patient who had who was unable to create speech, had a lesion in this part of the brain, just on the lateral side of the frontal lobe, and other patients with a similar dysfunction had a lesion in the exact same place. Then Wernicke came along and actually found that if a lesion occurred a little bit, let's see, don't know if I can actually get the pointer to work here. If a lesion occurred up in this area, you had the opposite problem where you could generate speech, but you could not understand it. You had receptive aphasia. And so this linking of function to specific areas became more active as a form of research, and people started to give up that hypothesis that the brain was uniform and interconnected, and realized that there were actually areas of function. So what makes up the brain? So the person who really got started in understanding how the brain works and found, surprised, that there were cells there, and it was going to be Carmelo Golgi. So he developed a silver stain that actually let people see the cells that were in there. Now, Schwann had said that the entire body is made of cells, and I think he included the brain, but the brain's very difficult to stain. It's not something that takes up other dyes easily. So this silver stain allowed him to see the organization of the microscopic brain. But in an interesting echo of the last controversy, his idea was that these cells formed a continuous network, and they were actually basically one big cell, because he never saw separation between them. In Spain, and we haven't mentioned Spain, Spain's been kind of a no man's land for medical science, but thank goodness we have Ramon y Cajal, because Ramon y Cajal did this silver preparation and actually spotted that there were gaps. There were synapses between these cells, and he meticulously charted out the stains, the processes, figured out that the dendrites and axons are arranged in a certain way and that they approached each other but didn't quite meet. And they both won the Nobel Prize, which I think had to be very awkward because they didn't really like each other. And so they both shared the Nobel Prize in the same year. And that's basically how we came to the idea that not only is localization of function happening grossly, but microscopically, just like the rest of the body. Now, Spain was kind of a no man's land, and sad to say, if that was bad, America was worse. America had had a good start with medical practice, medical hospitals, but when the Civil War came along, it just destroyed American infrastructure in a lot of ways, and there just weren't people. So many people had died. There weren't people to do all the work. Now, we had a fairly good start in Philadelphia. This is Samuel Gross, and he actually offered a course in pathology in Philadelphia. But after the Civil War, there was really just not much going on, and American medicine was pretty terrible. At that point, to be a doctor, you just really had to call yourself a doctor. I know that sounds pretty attractive right now for some of you. But you might, if you wanted to do better, train as an apprentice under another doctor, and you would just see whatever patients this doctor saw, and that was pretty much it. You certainly weren't going to be getting a lot of time in a hospital. You weren't going to be seeing a lot of variety. And the really high status medical training occurred in Europe. And so the wealthy would send their kids who wanted to be doctors to Europe. They would train in the various hospitals there, still relatively free form, wasn't really a standardized curriculum, but they would go there where actual science was being done and bring some of that work back to America. Now, who's going to be able to do that? Only the very wealthy. So where do they tend to be? They tend to be in large urban centers. So rural medicine in America was really pretty appalling at the time. In fact, it was pretty appalling just in general. And on top of that, when we talk next week, you'll notice that we didn't really have a whole lot to offer people. We didn't have a whole lot we could do to actually get people better. Surgery was kind of a gamble because you might die due to the surgery, you might die due to the infection. And pharmacology was very, very basic and probably more dangerous than it was effective. So when things changed in America and thereafter the rest of the world was with the founding of the Johns Hopkins University. Johns Hopkins was a railroad tycoon. He was a Quaker, and as a good Quaker, wanted to leave behind a legacy of something good. So he left railroad stocks behind to form the Johns Hopkins University and hospital. However, the stocks had lost a lot of their value by the time they finally got around to breaking ground on the hospital. And they realized they were not going to be able to fund it and basically run it the way they wanted to. At this point, the daughters and wives of the trustees of the hospital, or the eventual hospital, got together and said, we will raise all the money. We've got lots of contacts, we'll raise the money, but here are our stipulations. If you do this hospital and we get the money, A, you have to have it be postgraduate. This was unheard of. People had to have a degree before going into medical school. Sounds familiar, right? All the students had to be able to read French, German, and English because that's where all the work was being done. It was coming from Europe, so they had to be able to read where this actual research was happening. The school would be associated with a teaching hospital. The medical school would have standardized laboratories, standardized classes, and actual teaching in the hospital because the physicians who worked there and surgeons who worked there would be teaching their students. They were not allowed to have private clients, and the medical faculty had to work in that hospital, and that was it. And women were going to be admitted on the same basis as men. Which one of these things do you think was the real problem? Yeah, the last one. So eventually the trustees were like, okay, there's no other way for us to get the money. I guess we'll let women in. And the wives and daughters went about their business. They raised the money, relatively rapidly, and Johns Hopkins opened in 1893. Now I want to draw attention to that. The medical school opened in 1893. And radically would accept women as students. The first osteopathic school opened a year before, and look, there's women. So yay. Go osteopathy. Beat them to the punch. Actually, there weren't only women there were actually minority students too. I believe there were Indians and maybe also some African American students there, although I could be wrong on that. We'll have to double check before really stating that that's a fact. Now, Hopkins, though, became the major center for medical innovation, largely because it was in Baltimore, it was on the eastern seaboard, and it got a massive infusion of cash after something called the Flexner Report. We'll talk about that in just a second. But before that, I want to bring up pathology and how some of the work at Hopkins was really based around the founding faculty. A guy named William Welch actually was the person who was hired as their pathologist. He became a department chair and recruited in a lot of the other faculty who became major medical innovators. But he was no slouch himself. He described Clostridium welchii, which later became Clostridium perfringens, something you guys will hear a lot about. It's a pretty nasty bacteria. And trained a lot of students who went on to become Nobel Prize winners, and some people you may have heard of. There's Flexner, Walter Reed, came up with a lot of different procedures through his students and hired top-notch faculty to teach at the school. Now, I mentioned how American medical practice was really disastrous. So in 1910, the Carnegie Foundation commissioned a report called the Flexner Report. And it was written by Abraham Flexner, and he basically asked him to go around the country check out different medical schools and see what was working, what wasn't working, and what could be done to make the situation of medical education in America better. And so essentially he came back and said, it's all pretty terrible, but Hopkins is doing some really good stuff. Mayo actually had some good stuff going too. He gave a little bit of credit to Mayo. But he said, basically, the Hopkins model is the only bit of medical education worth keeping in this country, and that's what we should go for. And at that point, the Rockefeller Foundation chipped in millions and millions of dollars to have schools transfer to the Hopkins model with a teaching hospital, with dedicated clinical faculty. You can guess which one of those stipulations didn't actually make it. Women were not required to be admitted on the same basis as men around the country. But the results of the Flexner Report were kind of a mixed bag. Medical education became more uniform and better quality controlled. Basic science and laboratory teaching was mandatory, as was ward-based teaching in the hospital. Frauds and charlatans, people who were trying to peddle really ineffective snake oil or other kind of just concoctions, found it harder to operate, and unlicensed, unskilled physicians were largely run out of practice. However, running out the frauds and the charlatans is all well and good until valid medical professionals become classified as frauds and charlatans. And both midwives and osteopaths were in for a lot of trouble thereafter and had a lot of trouble staying in business after the Hopkins model was made universal. So the AMA became the dominant voice in medical education, and the AMA set about trying to get other groups put out of practice. So at that point, the MD schools in the country dropped to about 66 from over 130, and DO schools dropped from a relatively smaller number, 8 to 6. Now the good thing about the osteopathic schools is that most of them actually had some lab-based teaching. They were pretty decently run regarding anatomy, histology, and physiology laboratories, but again, not as consistent as we would hope. So the funding is one of the main things that really came about as the long-term driver for making MDs the dominant voice in American medicine up until about now. We're finally getting to the point where there's a bit of parity, a bit of visibility for DOs, but it's largely because funding was shunted to those MD schools that had adopted the Flexner model. And even though DO schools adopted a lot of the pharmacology that had been ignored earlier, once it became actually effective, that funding discrepancy remained and made it a little bit difficult for DO schools to get the same level of support. Now, we're going to jump ahead a little bit further because we've moved from this humoral imbalance of the entire body to locating diseases in organs, then tissues, then cells, but there are things in our body that are smaller than cells, and disease can actually be focused and located in those. And molecular biology and genetics really came into the forefront of medical practice and medical experimentation and research in about a 15-year span. So in 1940, George Beadle and Edward Tatum demonstrated that protein structure was somehow heritable. Now we say that heritable genes are involved. They didn't really know that genes were what we know they are now, but they knew that something about protein structure was inherited in subsequent generations, and that's something that would deal with keeping family lineages the way they are. 4 years later, Oswald Avery at the Rockefeller Institute tied that gene expression to DNA. Now DNA was something they'd known about for a long time. It was present in every cell. It was kind of cellular junk, as a lot of people thought about it. Think about albumin in the blood. That's kind of what people thought about DNA. Oh, it's just there to stabilize stuff. It's not really that important. And then, in 1953, using what we're going to call borrowed X-ray diffraction data from Rosalind Franklin, the James Watson and Francis Crick described that DNA had this double helix nature that actually was the basis for those heritable genes. Now I say borrowed here because there's a lot of controversy about whether they stole it, whether it was something she gave to them voluntarily, and Rosalind Franklin died of cancer not long after this happened, so she's not able to give us her version of the story, sadly. So, just FYI. Now we move a little further ahead into the 80s, and for the first time at University of Toronto, Lap Chi Sui, his team actually figured out that there was a specific disease caused by a specific gene mutation. This is the first disease that's actually given a genetic locus, and that's cystic fibrosis. If you have a mutation in this gene, you will get that disease, and that's that. And it can have a faulty protein pump, and you're going to wind up developing mucus in your airways because you're not able to pump ions and into the airway and pull fluid with it to clear that mucus. And so that's largely where we are now. Disease hasn't really gotten much smaller than genes. I think prions, we could kind of say prions are kind of a little bit of a smaller focus. But at this point, we're operating under this paradigm, and we've got some amazing things going. We'll bring up CRISPR and some other things of that nature a little bit later. But right now, we've found that disease can be located in all of these areas, and kind of really phenomenally, we've discovered that there are, in fact, some systemic diseases. Now, autoimmune disease has a locus where it originates, but it affects tissues throughout the body. You can have systemic diseases now, but we're coming back to that global view of the human body with a more sophisticated understanding of all the parts that are in play from the macroscopic to the microscopic. All right. So that's it for today. We've talked about what disease is. Next week, same time, same place, we will have a discussion of treatment. We know what disease is, so what were people doing about it this whole time? And I'm going to give you a quick preview by saying it was mostly terrible. Okay. Thank you very much. And thank you, Research Club.